Noémie Legout from Uppsala, who will tell us a beautiful story about Rabinowitz Floer complex for Lagrangian cobordisms.
Okay, thank you. Thank you for the invitation. I'm very happy to be in Paris and travel a bit after Corona. So yeah, I'm going to tell you about, so I'm going to define the Rabinowitz Floer complex for Lagrangian cobordism in some special setting, like with exact Lagrangian cobordism. So the goals of this talk are to, well, I will recall quickly what it is in a few minutes. But if I take two exact Lagrangian cobordism, sigma 0 and sigma 1 between Legendrian submanifolds, I want to define a Floer complex, a Floer type complex associated to the pair of cobordism, assuming they are transverse, which I will call 2 loop plus of sigma 0, sigma 1. And I will tell you how I define such a complex, some properties of this complex, and the goal, which I don't think I will go that far today, but the goal then is to define an infinity category whose objects are exact Lagrangian cobordism endowed with some augmentation of the negative end, but like some extra property. And so the object will be this non-compact Lagrangian, and the morphism spaces will be given by these Floer complexes. And then there will be also some A infinity composition maps. So basically this complex, I can associate to it a product and some a higher order composition map. So, okay, maybe I can just say a few words about defining an A infinity category associated to non-compact Lagrangian. It has been studied a lot already, like in particular, wrapped Fourier categories. So wrapped Fourier categories, like it's for non-compact Lagrangian, but in Liouville manifold. So in particular, it's a Lagrangian having non-compact cylindrical end on Legendrian, but like just a convex end. And this I should write some name, like many names. Abu Zaid Saidal, GPS, Ganatra, pardon, Shende. And I should say also that this, when you take two non-compact Lagrangian in this setting, in the Liouville manifolds, the Floer complex are defined using Hamiltonian techniques. So counting pseudo-holomorphic disk, satisfying a perturbed Cauchy-Riemann equation, perturbed by a Hamiltonian vector field. But then there is also Hekon-Lekili. They define wrapped Floer complexes associated to two Lagrangian in the same setting, but using SFT techniques. So counting curves with like counting a curve satisfying non-perturbed Cauchy-Riemann equation. But then you need to take a Lagrangian and a small copy of the Lagrangian in order to define it. So this is more like SFT technique. So today, what I'm going to do is like I'm going to consider as like not the setting of Liouville manifold, but Liouville cobordism. So our case. Liouville cobordism, meaning I will have like a non-empty negative end. But okay, Liouville cobordism in particular, I'm just restricting to the trivial one, which will be R times Y, where Y is a contact manifold. And I will consider Lagrangian submanifolds with a positive cylindrical end and also a negative cylindrical end. So, okay, the extra work is how to deal with the negative cylindrical end. And I should say that, like considering, okay, one more thing is I will use like SFT techniques, so not Hamiltonian techniques. And I should say that Oranchea, Silebach, they considered Lagrangian in some in Liouville cobordism and defined some Rabinowitz Floer homology groups for this Lagrangian, but assuming that the negative end of the Liouville cobordism is fillable. Assuming a filling of the negative end of the Liouville cobordism. And so in my case, and they use like Hamiltonian techniques. So in this case, I will have Liouville cobordism. I will not assume that the negative end admits a filling, but to compensate this, I will ask my Lagrangian cobordism to admit. I will ask that the negative end of my Lagrangian cobordism admits an augmentation. So maybe I don't have a lot of time to explain what this is, but I need some extra condition to compensate in some sense that I don't ask the fillability of the negative end. Okay, so that's what is going to happen. Let me recall very quickly what I mean by Lagrangian cobordism. So so as I said, I will consider the baby case of Liouville cobordism, which is just like the trivial one, so R times Y, where Y here will be the contactization of a Liouville domain. So in particular, so it's like P times R endowed with the one form dz plus beta. In particular, the Reb vector field is just dz, so I have no Reb orbit in this setting. It's just, no Reb orbit. Then an exact Lagrangian cobordism. From Lagrangian lambda minus to lambda plus in Y will be like a submanifold of R times Y, the symplectization of Y, with the symplectic form d exponential t alpha, where t is the coordinate on the factor R. And maybe I just draw a picture. So it's a submanifold such that there exists a real t. So when I intersect sigma with t plus infinity times y, I just have a cylinder over lambda plus. When I intersect it with minus infinity minus t times y, I have a cylinder over lambda minus. In between, I just want to have something compact. Okay, and then it's exact, meaning that there exists a smooth function defined on sigma, which is like the primitive of the one form exponential t alpha restricted to sigma. With some condition that f must be, like the function must be constant on the cylindrical ends, but I will not really need this now. I mean, I need it, but it's a technical condition. Okay. Oh, please, if you have any question, interrupt me whenever. Okay, so now I can tell you what is the complex I consider. So if I take, it's a bit too, okay, I take sigma 0, sigma 1, two exact Lagrangian cobordism which intersect transversally. And the complex associated to the pair sigma 0, sigma 1 is generated by three types of generator. The first generators are so this C of lambda 1 plus lambda 0 plus is the vector space, or let's say I'm doing everything on Z2 coefficient. So it's the vector space generated by red chords from lambda 0 plus to lambda 1 plus. The other types of generators are the intersection points, like transverse intersection points between sigma 0 and sigma 1. And the last type of generators are the red chords between lambda 1 minus and lambda 0 minus. So in the positive end, I consider red chords going from lambda 0 plus to lambda 1 plus. In the negative end, I consider red chords going from lambda 1 minus to lambda 0 minus. And intersection points. Okay. Plus some like shift in grading to make the differential degree 1 map. This is called the Cthulhu plus because the Cthulhu complex already exists. It has been defined by Chantraine, Dimitroglou, Rizal, Pizzini, and Golovko. So they have defined a complex associated to a pair of transverse Lagrangian cobordism, but with generators, also intersection points, red chords in the negative end from 1 to 0, and also red chords in the positive end from 1 to 0. So the only difference is the order of chords we choose at the positive end. And it changes actually some things. So the two complex, like this complex and their complex, they have some similarities, but also some differences. This sentence is quite useless. Anyway, okay, so I have a complex, I can define the differential. So as I said, I'm using SFT techniques, so the differential will be defined by count of pseudo-holomorphic disk. Yeah, I should. So okay, I forget. I'm always forgetting to say, but I'm always assuming everywhere that lambda 0 minus and lambda 1 plus admit augmentation. Epsilon 0 minus and epsilon 1 minus. So it's like, I don't know if like maybe not everybody knows what is an augmentation, but it's augmentation of the Chicano-Feliashberg algebra associated to the Lagrangian. And maybe if you don't know, just one thing to know is that if I have an augmentation, I will be able to send the red chord to some coefficient in Z2, like it's a map from the red chord to Z2 satisfying some properties. Yeah, maybe it will make sense probably when I define the differential now. In particular, also, if I have augmentation of the negative end, I can pull back this augmentation by a map induced by the cobordism in order to induce augmentation of the positive end. So once I have augmentation of the negative end, by the cobordism, I also have augmentation for this Lagrangian in the positive end. Okay, so the differential is a 3 by 3 matrix. And each component is defined by a count of pseudo-holomorphic disk. So the component, so there is a component going like, which takes as input a chord in the positive end and as output a chord in the positive end. And it will be defined by a count of strips with boundary on r times lambda 0 plus and r times lambda 1 plus. And it will count curves like this. So it's a strip with one positive red chord asymptotic. So it's a chord from lambda 0 plus to lambda 1 plus, which will be my input. And I have at least one negative asymptotic, which is a chord also from lambda 0 plus to lambda 1 plus, which will be the output chord. And I have possibly a lot of pure red chords asymptotic. So pure red chords of lambda 1 plus and lambda 0 plus. That I can, okay. Okay, I have possibly a lot of pure red chord asymptotics that I transform into a coefficient in Z2 using my augmentation. So my map will take this positive chord and spit out this negative mixed chord, and the other negative red chords becomes a coefficient in Z2 using the augmentation. Okay, and this chord, this curve is like index 1 curve because it has boundary on the cylinders r times lambda 0 plus and r times lambda 1 plus. Okay, so I mean, it's going to be the same type for all the other components of the differential. The components taking as input a chord in the positive end and as output an intersection point will count disk with a positive, so a positive red chord asymptotic and another asymptotic to the intersection point. So it have a curve like this of index 0 with boundary on the compact part of the cobordism. So boundary on sigma 0, sigma 1. The input is the chord, the output is the intersection point. And the last component in the first column take as input a chord in the positive end and as output a chord in the negative end. So then I will count, so I will have a strip with positive red chord asymptotic. Then like a strip with boundary on the compact part of the cobordism and a negative red chord asymptotic, which in this case, the negative red chord asymptotic is the chord from lambda 0 minus to lambda 1 minus, which is not a chord of the complex, because in the generators of the complex in the negative end are chords from lambda 1 to lambda 0. So I glue to this strip a banana. So a disk with two positive red chord asymptotics, and the other positive red chord is a chord from lambda 0 minus, no, sorry, for lambda 1 minus to lambda 0 minus. And this is the output of the map. And this banana, so it's a rigid banana, but it has index 1 because it has boundary on cylinders r times lambda 1 minus and r times lambda 0 minus. Okay, and then, okay, the other components are defined accordingly. Like the component from the intersection point to itself, it counts like usual Floer strips, and then etc., etc. Component from like here, I will also have some. I will also need the banana map from the component to intersection point, from intersection point to red chord in the negative end, and then okay. I mean, you see what I mean. and I have some, finally, some curve like this. Okay. So that's my differential, input here and out. Okay, this like the first term on the second and third column are 0 for some action reason, like our energy reason of pseudo-holomorphic disk. Okay, so that's for the differential. Like, okay, so I define this map and M1 square equals 0. How to prove this? It's like the usual, like a usual argument with pseudo-holomorphic disk. I have this map. I want to prove that M square equals 0. So I look at, so index 1, or like a one parameter family of pseudo-holomorphic disk. I look at how this disk will break, or in other words, I look at the boundary of the compactification of the modular spaces, and it will give exactly the term appearing in M1 square. And I'm counting everything over Z2, so I don't care about signs, and it gives M1 square equals 0. In this argument, I also need that. I also need some properties of the augmentation, but so the augmentation play an essential role. Otherwise, it would not work. Okay, I can maybe give you a like easy example of this complex in a case where there's just one type of generators. Let's say, so example, if I take a Legendrian, lambda 0, and then I take lambda 1 to be a very far push off of lambda 0 in the positive rep direction. So it's, I take lambda 1 to be like a translation in a positive rep direction, and then I perturb it by a Morse function so that I have just a finite number of rep chords between lambda 0 and lambda 1. So in this case, if I look at the Cthulhu complex associated to the Lagrangian R times lambda 0, so to the cylinders R times lambda 0 and R times lambda 1. In this case, I just have, like, I don't have intersection points. I don't have chords from lambda 1 to lambda 0, but the only chords I have are from lambda 0 to lambda 1. So there is just one type of generators, which are chords from lambda 0 to lambda 1. And the differential is just given by the first term in the first column on of this matrix here. So it's, for people who know, this type of curves, like having input as positive rep chord asymptotic and rep chord differential of the bilinearized Legendrian contact homology, associated, like restricted to mixed chords from lambda 0 to lambda 1. So it's like the differential is the differential of bilinearized by augmentation, bilinearized Legendrian contact homology. In particular, it's this complex. In the case of this 2 copy of Legendrian, it's exactly the complex of the 2 copy considered by Ekholm, Etnayer, Sabloff in the paper about duality exact sequence for Legendrian contact homology. Okay, so now what are the properties of this complex? So I will like focus on three main things. The first is that in the case So I said there is this complex, this Cthulhu complex defined by Chantraine, Mitroglou, Rizal, Ghigini, and Golovko. This, their complex is, in the case of, when I consider Lagrangian in the symplectization of a contact manifold, it's always acyclic, but this complex Cthulhu plus is not always acyclic, but in some cases it is, and it's given by the following. So if the pair lambda 0 minus lambda 1 minus, or the pair lambda 0 plus lambda 1 plus is horizontally displaceable, then the complex is acyclic. So what does it mean that the pair lambda 0 minus lambda 1 minus is horizontally displaceable? It means I have my two Legendrian, and I can apply some Legendrian isotopy in such a way that there are no red chords anymore between lambda 0 minus and lambda 1 minus. So in this case, the complex will be acyclic. So there are explicit examples where the complex is not acyclic. It happens. Second property is that I can define a product and an A, like a higher order composition maps. So like A infinity, I have some A infinity composition maps. And the last thing is that there is existence of a continuation element. So I call continuation element something that I would like to be a unit. So what I mean by this is that if I can define the Cthulhu complex associated to cobordism sigma with itself, I would like to have an element in this complex Cthulhu of sigma sigma, which will be a cycle and satisfy that when I multiply with this element, I get the identity map. But of course, I have defined the complex associated to a pair of transverse cobordism. So that's why I call it continuation element. But anyway, okay. It will be in the complex associated to a cobordism and a very small perturbation of the cobordism. Okay, so let's have a quick look at the first property. So in order to prove this, in order to prove this acyclicity in case of horizontal displaceability, I need some properties of the complex with respect to concatenation of cobordism. So if you have like a two cobordism, like let's say W0, which has a positive end lambda 0 plus and negative end on some lambda 0, then I have if I have another cobordism with positive end, a cylinder on lambda 0 and negative end on lambda 0 minus, I can concatenate both to get a cobordism from lambda 0 minus to lambda 0 plus. So I call the bottom one V0. Then I take a pair of concatenated cobordism. Like V1 concatenated with the W1. And I can associate to this pair of concatenated cobordism the complex, so associated to V0 concatenated with W0 and V1 concatenated with W1. And this, so this complex has 4 types of generators: the chord in the positive end, the intersection point between W0 and W1, intersection point between V0 and V1, and chord in the negative end. And the differential is defined in terms of the differential of the Cthulhu complex of the top, the differential of the Cthulhu complex of the bottom, and some maps, which I call transfer maps, which are maps going from the complex associated to the pair of concatenated cobordism to the complex associated to the pair of the bottom, V0, V1, and another map going to the complex associated to the pair in the positive at the top, W0, W1. So I have two maps that I call delta 1 and B1. And these maps are actually chain maps. So I can prove that delta 1 and B1 are chain maps. And so once I have this structure, I can concatenate cobordism in the following way. So assume that, okay, let's assume that the pair lambda 0 minus lambda 1 minus is horizontally displaceable. So in this case, I look at, so I have my complex associated to the pair of cobordism sigma 0, sigma 1. Then what I can do is, so in which order I do it, I can wrap the positive end of sigma 1 in the negative red direction. So I don't move sigma 0. Sigma 0 is still the same. And sigma 1, I will wrap the positive end in such a way, so in the negative red direction, in such a way that there are no red chords anymore between lambda 0 plus and lambda 1 plus. So there are no generators anymore in the positive end. So, and when I do this, when I wrap this positive end, so you see that now I have like, I can view this as a concatenation of two cobordism, my original cobordism, plus a trivial cylinder and the wrapping of R times lambda 1 plus. And so from this pair of concatenated cobordism to my original pair, I have this transfer map, delta 1. And I can prove that by this operation of wrapping, this map is actually an isomorphism of complexes. So these two complexes are isomorphic. Then I do the same trick in the negative end. Now I take this pair of cobordism that I have, and I will wrap the negative end of sigma 1 in the positive red direction in such a way that there are no red chords anymore between lambda 1 and lambda 0. And by using the other transfer map, B1, going from this last pair to the pair just before, it's an isomorphism by this wrapping operation. Now, if you look at like what I get here, I have a pair of cobordism, and the Cthulhu complex of this pair has just one type of generators. It's just the intersection point between the two cobordism, because I don't have red chords from 1 to 0 in the negative end, and I don't have red chords from 0 to 1 in the positive end. So this complex has just positive intersection point generators. And now I apply some, then I prove that the complex is invariant by compactly supported Hamiltonian isotopy. So I take this red sigma 1 and I just, like by a compactly supported Hamiltonian isotopy, I push it far to the right in such a way that, so I push it far to the right in order to move all the intersection points somewhere in the negative end. So in such a way that all my intersection points arise in the negative cylindrical end, in some sense. So after that, my complex is just given by like some intersection point between a trivial cylinder and a cylinder which is wrapped around this white cylinder. But then I can just like this pair of cobordism, so this pair of like cylinder and a wrapped cylinder, the complex associated to it is actually isomorphic to the complex associated to this trivial cylinder original one and the non-wrapped trivial cylinder over lambda 1 minus. By wrapping also by using some transfer map. So at the end, what I have proved is that the Cthulhu complex associated to my original pair of cobordism is like homotopic to the complex associated to this pair of trivial cylinders, where here my lambda 1, like my lambda 0 minus is far above the lambda 1 minus in the positive red direction. But then I have the Cthulhu complex of this pair of cylinders is just generated by chords from lambda 1 minus to lambda 0 minus. So I have just chords from lambda 1 minus to lambda 0 minus. But then the Cthulhu complex in this case is just like the differential. The differential is the differential of the bilinearized Legendrian contact cohomology. In this case, I'm going from top to bottom anyway. But then, so it's the complex also considered in the by Ecole, Metnayer, Sabloff. And I'm using the fact that Legendrian contact homology is invariant by Legendrian isotopy. So I take these two cylinders, and by assumption, lambda 0 and lambda 1 are horizontally displaceable. So I can just move one, like let's say I move lambda 0, 1 by Legendrian isotopy, like very far on the left or on the right or whatever. And then there is no chord anymore. So the complex is just 0. There's no generators. Okay. But, yes.
So you need to assume that both pairs are horizontal.
No, actually, I just need one.
I thought you used both.
But here I just, no, I mean, I just used that lambda 0, lambda 1. I mean, I just, by this, all this like sequence, I proved that the complex associated to original pair is isomorphic to the complex associated to this cylinder over lambda 0 minus and lambda 1 minus. Here I say like I have this complex where I push down all the intersection points between, I push them down so that it becomes just intersection points between the cylinders in the negative end. So when I look at this complex, the only generators of this complex are these intersection points in the negative end. So I can just forget the top, like I don't, it's not part of the complex.
But in the picture that's on the first line to the right, the one that is the source of V1. The source of V1.
Here.
Right? There you displaced on the bottom, and first you displaced on the top.
No, but here I don't displace, I just wrap. But I don't assume that I can move so that there is no, so that I don't assume that I can horizontally move. I just wrap along the red vector field, along. Okay, yeah. But then, of course, so for example, if I am here at this step when I have wrapped the negative and positive end, if instead of assuming lambda 0 minus and lambda 1 minus are horizontally displaceable, but I assume that the plus are horizontally displaceable, then I will take like compactly supported Hamiltonian isotopy that will push all the intersection points in the positive end.
Oh, so you use, for example, displace infty at the very end?
Just at the very end. Yeah, exactly. Yeah. Yeah, exactly. Yes, no problem.
quantization. Like you get to this like
yeah. Or if you work in if you take I mean, if you take the Legendrian to be zero section of the one jet space, then it's not horizontally displaceable. So yeah, if you take cobordism between Legendrian in jet space that like wrap around the zero section, or then it will not be acyclic because it will not be displaceable. Yeah, it's like it's. Okay, I think I should say that it's more like so. If you have like two Legendrians, I say that the pair of two Legendrian is horizontally displaceable if I can. I take this one and I can move it by Legendrian isotopy. So, for example, I take Legendrian isotopy that move it here, like just far on the right, in such a way that I don't have any red chords anymore between the first one and the second one. Yeah. Okay. So this was for the first property. Okay, maybe okay, I will try to go a bit quickly. Okay, the other thing I said is that this complex is endowed with product structure and like A infinity composition maps. I will just focus on the product, like I'll tell you quickly what I mean by this. So if I want to define a product, I need to take like 3 exact Lagrangian cobordisms, which are pairwise transverse. And then I will define a map, M2, from the Cthulhu complex associated to sigma 1, sigma 2, tensor the Cthulhu complex associated to sigma 0, sigma 1, to the Cthulhu complex associated to sigma 0, sigma 2. And this, so basically this map will just be defined by counting all the possible rigid configuration of curves that take 2 inputs in the Cthulhu complex and like splits another mixed, like a generator of the Cthulhu complex of sigma 0, sigma 2. Okay, when I say I count all the possible rigid configuration, I can just give you one example. So if I take like a red chord in the positive end in this first factor sigma 1, sigma 2, and a red chord in the positive end in the Cthulhu complex of sigma 0, sigma 1, sigma 2 first, and sigma 0, sigma 1 after that. So I have 2 red chords, gamma 2, gamma 1. And the product will be defined by a count of several types of curves. For example, so the components that will take these 2 chords, gamma 2, gamma 1, and take values in the chord in the positive end of sigma 0, sigma 2, is defined by a count of curves with boundary on the positive cylindrical end, having like positive asymptotic to gamma 1 and gamma 2, and a negative asymptotic to a chord from lambda 0 plus to lambda 2 plus. And the red here is lambda 1 plus. So the output is a negative red chord asymptotic. But it's not the only way. So when I said all the rigid configuration, I mean that, so this type of curve is not the only rigid way to associate to 2 positive chords a negative chord. The other ways are the following. I take gamma 1 and I consider like a banana disk with boundary on the compact part of the cobordism. So with 2 positive red chord asymptotic, one on gamma, 1 and another on a chord from lambda 1 plus to lambda 0 plus. And I attach to this one a disk with boundary on the positive cylindrical end, having one positive asymptotic to gamma 2 and another negative asymptotic, which is my output. Okay, so this is with boundary on the positive end, and this banana is with boundary on the compact part of the cobordism. So this is rigid of index 0, this is rigid of index 1 because of translation. And I say it's a rigid configuration because I cannot, there's no way to glue these two curves. These two curves together, they do not form a pseudo-holomorphic building that you can glue. Okay, that's why I say it's rigid, or we could say it's a partial holomorphic building, something like this. Okay, etc., etc. I will not draw more curves here, but yeah, all the possible rigid configuration you can find, you have to count it in the definition of the product. Okay. And again, this, so I say it's a product, meaning that I wanted to satisfy the Leibniz rule, which is like M2 of identity tensor M1 plus M2 of M1 tensor identity plus M1 composite M2 equals 0, and again you get this identity by looking at like all the moduli spaces involved in the definition of this product. I look at the boundary of the compactification, and all the terms together I sum it, and it gives the Leibniz rule with some small subtleties that sometimes I look at like a moduli space, I compactify it, I look at in the boundary all the possible broken disk I get, and some of them do not contribute to the Leibniz rule, but they cancel with some other broken disk appearing in the boundary of the compactification of another pseudo-holomorphic of another moduli space. I can give a very quick example. If I take this disk, this moduli space of disk of curve, like a disk with two positive red chord asymptotic and one negative red chord asymptotic, I take this disk, so I take it of index 2 with boundary in the positive cylindrical end. So it's like it's the same as if I take a one parameter family of such disk, then it can break into like a two-level building, both with boundary in the positive cylindrical end. One will have, like the top level will be a disk with one positive red chord asymptotic and two negative. And the lower level will be a banana with two positive asymptotic, glued to one of the negative of the top one. So both of index 1. This appears in the boundary of the compactification of this moduli space. But this is not in the Leibniz rule. This term is not like in a product times blah 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 differential, but it appears in the boundary of another moduli space, which is the following. So which is like a configuration of two disks that do not glue together. The top one is a disk in the positive cylindrical end with one positive asymptotic and two negative red chord asymptotic, and then a banana, again in the lower level, but a banana not with boundary in the cylindrical end, but with boundary in the compact part of the cobordism and of index 1. Okay, so this term, this is not rigid because here I have an index 1 banana with boundary on like some non-cylindrical part. So this moduli space of bananas has to be compactified, and this configuration appears in the boundary of the compactification of this, but also of this. So it appears twice, so it cancels. So it's not a problem that this does not appear in the Leibniz rule, because it just cancels by itself, like with some other things. That's the only really like subtleties, let's say, that happen. Okay. So I'm of course a bit late. Okay, the last thing I want to discuss is this continuation element. So as I said at the beginning, the idea would be if I define two loopers of sigma with itself, I would like to have like a unital complex. So I would like to have an element E in this complex, but I have not defined what is Cthulhu of sigma with itself. So instead, I will take a cobordism sigma 0, and I will take sigma 1 to be a small perturbation, so well chosen of sigma 0. And then I will define an element, E, which is called E sigma 0, sigma 1, in the Cthulhu complex associated to sigma 0 and sigma 1, which will satisfy the following. So it will be a cycle. So M1 of this element is 0. And M2, so if I multiply, let's say on the left, no, on the right, by this element, so M2 of something and this element will be a map from Cthulhu plus of sigma 1, sigma 2 to Cthulhu plus of sigma 0, sigma 2. I want this map to be an isomorphism. Okay, so it kind of mimic the properties of unity. Because, yeah. Okay, so what is this element? So I have my cobordism sigma 0, and how do I what do I take for sigma 1? So I take sigma 1 to be the graph of a Morse function in a standard neighborhood of my sigma 0, in such a way that I take sigma 1 to be like this small perturbation of sigma 0, in such a way that so the critical point of the Morse function f, so I take a Morse function f defined on sigma 0. The critical point of the Morse function are in 1-1 correspondence with the intersection point of sigma 0 and sigma 1. And I take this function f in such a way that lambda, so the cylindrical ends of sigma 1, so lambda 1 plus or minus is like the Morse perturbation, like how do I write this? It's a Morse perturbation of lambda 0 plus minus minus delta dz. So what does it? So by a Morse function f plus minus defined on lambda 0 plus minus. So it means I have my lambda. So I have my lambda 0, and I take a very small push off in the negative rep direction, and I perturb it by a Morse function. That will be my lambda 1. So I take this lambda 1, this sigma 1, and the continuation element E sigma 0, 1 will be the sum of the maxima. So it will be E0 plus E minus. E0 is the sum of the maxima of the Morse function big F, and E minus will be the sum of the maxima of the Morse function F minus, which I use to perturb lambda 0 minus. Maybe it can look weird that it's a sum of maxima instead of a sum of minimum. That maybe sometimes is more common, but it just depends on the convention of which Lagrangian you wrap in which direction. And in this case, I chose this, and it happened that it was a sum of maxima. But anyway, I guess I should stop soon. What could I say to finish? So, okay, now that I defined this, I should show, okay, my plan was to give some idea of proof of why this is actually a cycle and why multiplication by this is an isomorphism. Maybe I can, okay. Maybe I can give you one first idea of why it's a cycle. In some case, like in 2 minutes, if I assume, so for simplicity, I assume that my Lagrangian are connected and that the negative cylindrical end is not empty. So I can take a function big F so that it has no maxima in the interior. And my continuation element would be just a sum of maximum red chords in the negative end. So it would be just this. And let's say if I want to prove that this is a cycle, so I want to prove M1 of E minus equals 0. So this is by definition of the differential, I can write it to be M1 0 of E minus plus M1 minus of E minus, meaning the component of like the differential M1 of E minus is just like a component with values in the intersection point and with values in the negative, in the chords in the negative end. And if we have a look, so we prove that M1 0 of E minus equals 0 and and M1 minus of E minus equals 0 also. And so, for example, if I look at M1 minus of E minus, which types of pseudo-holomorphic disk this is counting, it counts like a disk, like strips with a negative red chord asymptotic to E minus and a positive red chord asymptotic to some chord beta, and with boundary in the negative cylindrical end. Now, like I distinguish two cases. The first case is if beta, the positive red chord asymptotic, is a Morse chord. So if it's a Morse chord, meaning if it corresponds to a critical point of the Morse function F minus, then for some action reason, there are no pure red chord asymptotics possible. So it's just a strip, and which will actually correspond. So this strip is in one-to-one correspondence with negative gradient flow lines of F minus flowing, so from the maximum E minus to an index n-1 critical point of F minus. And then my Lagrangian lambda 0 minus is compact. So every time I take an index n-1 critical point, there are exactly two flow lines that will flow from a maximum to beta. And if it's not the same maximum, it doesn't matter because E minus is just the sum over all the maxima. So like beta will have contribution 0 because I have those two lines. Okay, maybe I will just stop here. It's just an idea of all this kind of all like, yeah, this kind of arguments that I use to prove that this is a cycle, and it's approximately the same type of arguments, but with 3 copies to prove that the multiplication by the continuation element is an isomorphism. But okay, thank you. I'll stop here.
What would you like to do with this? So
What would I like to do?
You have applications in mind. What is better about it than the standard series for Chandru, Fluorology?
Sorry, what did you say after that?
So you want to do something with it, right? About genres or chords or?
That's a good question. Yeah, I don't really know yet. I mean, yeah. But yeah, I don't know. There are things to understand. There are things that I would like to understand. It's not necessarily an application of this. Oh yeah, maybe I forgot to say that I realized not so long ago that this complex has actually exactly the structure of an A infinity arity triple, which appeared in Alexandru and Kai's paper. And it seems like you define some Rabinowitz homology groups using this A2 arity triples or something like this. And for example, so they define it this way with like Hamiltonian techniques. And I don't really see, there is necessary some strong relation between both, like this SFT definition and this Hamiltonian definition that I have not really understood yet, but maybe some other people understand it very well already, I don't know. But that's not necessarily an application. It's just something I would like to understand. But yeah.
I had a question. So if you apply to sigma 0 equals sigma 1, that 3 by 3 matrix would be lower triangular.
Would be what?
Lower triangular. Because in your 3 by 3 matrix that you wrote for the differential,
yeah,
there's two entries which are 0.
Yes.
But it's not lower triangular. There's something.
Yeah.
Like which takes a constant and spits out a square from lambda 1 to lambda 0.
Yeah. Depending on the perturbation, if I define a Cthulhu of sigma with itself to be Cthulhu of this pair, but I should check. I never remember. Yeah, there is one way, probably this way that there are no positive action intersection point, and then it would be lower triangular. Oh yeah, it's exactly, yeah, it's wait, no. I'm not. Yeah, I think so. Yeah, I think so. No, I'm not sure. Maybe one way to make it. Oh yeah, there is one way to make it. Yeah, sure. Yeah. Oh yeah.
I don't know. In the usual tool, in general, it's not.
No, but
talking about this tool, which is the real tool.
no, but even no, but no, but Paulo, even in your.
I'm just trying to compare this with whatever I imagined from the setup. So I was double checking whether that.
But I mean, in this Cthulhu or in your Cthulhu, you can just if you choose one, you can choose one perturbation in such a way that is yeah.
The perturbation which made one of the two.
Yeah.
I mean, it can be made a cone in different ways.
Yeah. But
if you don't choose the perturbation carefully, it's definitely not a code.
yeah. But if you choose it,
A double code.
Yes.
yeah.
Other questions? Max?
This condition about displaceability, what is it? Is it generic or is it almost never fulfilled? Or
This condition of for it to be triangular or not, it's just a matter of no. I mean, you have quite some possibilities. It's just a way to, yeah. You have to choose the Hamiltonian in such a way. Like I never remember. Like if you choose the Hamiltonian positive, then you can describe like this is like exact Lagrangian cobordism. So you have a primitive here, and like you can describe the primitive of sigma 1 by the primitive of sigma 0 plus some term coming from the Hamiltonian. And then the action of intersection point is given by f1x minus f0x. This is the action of an intersection point. So then if f1 equals f0 plus some like a positive, like some Hamiltonian which is positive in the compact part, then you can make like you have some possibilities to you can make all intersection point become negative action or positive action. Like yeah, it's I mean it's doable depending on which Hamiltonian you choose. But of course, if you take like random Hamiltonian, usually you will have negative action intersection point and also positive action intersection point. But yeah, because it's just in the differential, there are like some curves like this, so negative red chord asymptotic and intersection point, and there are curves like this, like this, like intersection point chord and a banana. And when you have an input which is a negative chord and output an intersection point, this the differential increases action. So if I have a curve like this which exists, it means that this output intersection point has to be positive action, and this it has to be negative action. So if I manage to cancel all the negative action or all the positive action, one term of the differential will not exist and be zero. Yeah.
Go ahead, Adi.
Related to some graph category, because you said you have an infty category.
Yeah. So yeah, I would say yes, but it's not at the Rab-Foucault category. As it is defined now, it's not defined. I mean, it's defined for have a non-empty concave end, but well, I think. Yeah, for example. Yeah, if I restrict to, well, I don't know, like, yeah, if I restrict to fillings, to Lagrangian fillings, and Rab-Foucault is defined for yeah, like for like Liouville cobordism with non-empty concave end, it should give at least quasi-equivalent categories at the end. Yes. Oh.
So I'm sorry, it's a question which I know the answer, but I think it's something you should have said. So what do you need to go from, I mean, this is a particularly restrictive case, the symplectization of compactization. what is missing to do the something more general?
I mean, not in a symplectization or not in a symplectization of a complexization.
But for example, but not in the symplectization of complexization. So we'll go to more
Symplectization of something else.
No, I mean, you will cobordism, and you will cobordism.
But for example, you could have some Reb orbits. In this case, there are no Reb orbits at all. So I would have to consider some. I guess I have to consider this like on-chord, like is it the word on-chord disk? When you have some, like you count disks that could have like some negative asymptotic to some Reb orbits, and then you have to fill it. That's one thing to deal with. But Paulo, you know the answer. You have probably more things than me to say about this.
Maybe it's a good topic to discuss. But I'm interested in that. I don't know. But if I may rephrase your question, it is what's missing in order to do this for an arbitrary conductor, not for a conductization. Yes.
Or not for a symplectization.
How to work in the presence of closed red orbit. That's it.
Yeah, yeah, I'd say the real step. I mean, first of all, if you believe that it's claimed in the subject, that's really nothing. You know, this theory can be reflected word by word in the general sense. Yeah. But you have to believe a bunch of things which not everybody believes. Or I don't want to wait.
Yeah, you have to take it. For someone that here's a building, the building is already big.
Yeah, exactly. And what I say, you know, it's in some sense, I mean, there's nothing more to add as we parts. So there's nothing more to add, assuming that polyforms work as they expect. Yeah. But if you want to do it with more downward techniques, then I agree that the big step is going from the contactization to general contact. From a cobordism, from a symplectization to cobordism, that should be a relevant step.
Here's a broad issue. The complexity there is like the counts to add up to.
Yeah, I mean, moving from precise,
But yeah.
But it's really the usual problem of mathematical problems.
If I may, I'm not sure that the people who are watching out there do understand our discussion because we're not speaking loud enough. So I suggest